Welcome to the deep dive. Today we're getting into a paper from ByteDanceSeed called Scalability of Simplicity, Empirical Analysis of Vision Language Learning with a Single Transformer.
That's right. They introduced a model called SAIL, Single Transformer Model for Vision and Language.
And the big idea here is, well, simplicity. It's a single transformer handling both raw image pixels and text directly.
Exactly. It ditches that separate vision transformer, the VIT component you usually see in modular, multimodal, large language models, or MLLMs.
So no separate encoder. That's the hook.
That's the core innovation. And the headline finding is that SAIL performs comparably to those big modular models.
But it gets better, right? They talk about scalability.
Yes, superior data scalability, which is huge. And it shows this interesting vision-centric information flow.
Plus, it actually works really well just as a vision encoder on its own.
Surprisingly well, even competing with things like VIT22B on tasks like semantic segmentation. It's quite something.
Okay, so this simpler design could really change things for multimodal AI. Let's unpack this, really get into the nuts and bolts.
Absolutely. For a while now, the standard way, the modular way, has been, taking a pre-trained vision model,
like a CLAP or a SIGLIP VIT.
Exactly. And then using a separate large language model and sort of gluing them together with a projector. Think LVA.
And that works. I mean, we've seen good results.
It does work, but it's fragmented, right?
Yeah.
You're processing vision and language separately at first, and you're really dependent on how good that initial vision encoder is. Scaling can be tricky.
So SAIL is trying to bypass all that, a truly end-to-end integrated system.
That's the philosophy, just one unified architecture.
Okay, so let's get into SAIL's architecture then. What's under the hood?
At its core, it's one transformer network. It takes in both image patches and text tokens.
How does it handle the inputs? Text to standard, I assume.
Pretty much. Tokenization, then embedding. For images, they partition the picture into fixed-size patches.
Like VIT does.
Yep, similar idea. Then those patches get linearly projected into embeddings.
Okay, so you have image patch embeddings and text embeddings. How do they combine?
This is neat. They introduce special tokens, vision and vision. These basically bracket the sequence of image patch embeddings.
Ah, so they mark where the image data is within the sequence.
Exactly. Then you just concatenate the text embeddings and the bracketed visual embeddings.
And feed that whole sequence into the transformer layers.
That's it. And the crucial part is the self-attention mechanism inside those layers works across both the text and image tokens simultaneously.
So no separate projector module trying to align features?
Nope. The cross-modal interaction happens deep within the unified attention layers. Much simpler.
Simpler, yes. But how does it actually compete without specialized components? What are the key innovations that make SAIL work so well?
The paper points to two main things. First is what they call the mixed attention mechanism.
Mixed attention, how does that work?
Well, think about text. For generating text, you need causal attention, right? Tokens only look back at previous tokens.
Standard autoregressive setup.
Right. But for an image, you often need to understand spatial relationships between patches, seeing the whole picture.
So causal attention isn't ideal for the visual part?
Probably not optimal. So SAIL does something clever. Text tokens use causal attention, preserving the generation ability.
Okay. And image tokens.
For image tokens within the same image, they use full bidirectional attention. Patches can attend to all other patches in that image.
Ah, so it captures that holistic spatial context within the image.
Precisely. It allows for much richer interactions and understanding of global dependencies in the visual data. This is a key difference from some earlier single transformer models that mainly stuck to causal attention.
That makes a lot of sense. Different data types, different attention needs. What's the second innovation?
The second one is Multimodal Rotary Position Embeddings, or MROP.
ROPE, okay, we see that in LLMs.
Yeah.
How is it multimodal here?
Standard positional embeddings often treat everything as 1D, which isn't great for 2D images. MROP tackles this.
Oh.
It decomposes the position for image patches into separate height and width components.
So it's inherently 2D aware for the visual part.
Exactly. Text tokens still use the standard 1D ROPE. But for image patches, the height and width IDs get adaptively mapped to the token's actual 2D coordinates.
Adaptive mapping. Does that help with different image sizes?
Yes, that's a big benefit. It aids generalization to different resolutions and aspect ratios. They also initialize the position indexing sequentially across modalities.
What does that mean, sequential initialization?
Like maybe image patches get indices 1 to n, and then text tokens start from n+1. It helps maintain some consistency in the overall sequence.
And the benefits of MROP overall?
Better sensitivity to the 2D positions in images, And it also helps constrain the absolute position magnitudes for visual tokens, which seems to help generalization. Big plus for handling various image inputs.
Okay, so mixed attention and MROP are the architectural keys. Let's shift to training. How do you train one model to be good at both vision and language?
They use a smart two-stage pre-training curriculum. Stage 1 is all about accelerated visual knowledge acquisition.
Sounds intense. What does that involve?
Pre-training on a lot of image-text pairs, 512 million total, using datasets like Recap Data Comp 1B and also text from Slim Pajama.
512 million. And what about the images?
In this first stage, they use a lower resolution, 224 by 224. This speeds up training, lets them push more data through faster.
And why the pure text data, the Slim Pajama part?
Crucial point. They interleave it to prevent catastrophic forgetting of language abilities. You don't want the model to become only visual.
Makes sense. Keep the language skills sharp. What happens in stage 2?
Stage 2 focuses on enhancing understanding at native image resolutions. They call it the NES strategy.
So handling images as they come without resizing down.
Exactly. They continue pre-training, but on a smaller, curated set of about 86 million pairs. Things like Cat Fusion, OCR data, Infinity MM subsets.
And MROP helps handle those varying resolutions dynamically.
That's the idea. This stage is more about fine-grained details. Text in images, tables, complex layouts.
Still mixing in text-only data.
Yep, still interleaving Slim Pajama to maintain language grounding.
What's the actual learning objective during pre-training? Is it complex?
Surprisingly simple, actually. It's just the standard language modeling loss. Predict the next text token.
Only on the text tokens, not on the image patches.
Correct. The loss is only calculated on the text tokens. The image patches in those special vision tokens are excluded from the loss computation.
Wow. So the visual understanding is learned implicitly just by needing to predict the related text.
Exactly. It's forced to learn meaningful visual features to be good at the language task. It's quite an elegant approach, mirroring how we often learn about visuals through language.
That is fascinating. Okay, so after these 2 pre-training stages, what's next? Fine-tuning.
Right. The whole network then goes through supervised fine-tuning, SFT.
Using what kind of data?
Mostly instruction-following datasets, like the Infinity MM Stage 3 subset. About 6 million image text pairs, again processed using NERs.
And the goal of SFT here is
to align the model better with human instructions, make it better at complex queries, dialogue, really leveraging both modalities in conversation.
Okay, architecture, training. Sounds solid. Now the proof is in the pudding. How did SAIL actually perform?
They really threw the kitchen sink at it in terms of benchmarks. A whole battery of tests.
Yeah, like what?
Standard vision language stuff.
And?
MMBench, SeedBench, MMVet, MME. Also things testing for hallucinations like Illusion Bench, math reasoning with Math Vista Mini, OCR benchmarks.
Text VQA, Science QA.
Yeah, AI2D, MM Star, Real World QA, a really diverse set.
So how did SAIL do against other single transformer models first?
It consistently outperformed them. Models like Fuyu, EVE, Solo, Mono Intern VL, EV2.
And it did this without extra bells and whistles.
That's what they highlight. No complex add-ons or auxiliary losses that some others use, just the core architecture.
Impressive. Okay, the big comparison. How did it stack up against the state-of-the-art modular MLLMs like LFA?
Here, the results were comparable on several key benchmarks. Things like MM Star, SeedBench IMG, Real World QA.
Comparable, but maybe not uniformly better yet.
Exactly. The authors acknowledge there's still a gap in some areas. Their hypothesis is that more pre-training data, or maybe higher quality instruction tuning data, could close that gap.
That makes sense. It's still a relatively new approach compared to the years of work on modular systems.
Right. But achieving comparability with this simpler design is already a big statement.
Definitely. And didn't you mention it also functions well as just a vision encoder? How did they test that?
Yeah, this was another really interesting part. They evaluated as visual representations on purely vision tasks.
Like image classification.
The InterNet 1K, yes. Yeah. And semantic segmentation on ADE 20K. Plus, compositional understanding on the ARO benchmark attributes, relations, ordering.
And the results there.
Quite striking. On ImageNet, nearly 85% top 1 accuracy, over 97% top 5. That significantly beats other encoder-free approaches.
Wow. And segmentation.
On AD20K, you got an MIOU of 55.3%. That's really competitive with dedicated vision backbones like OpenCLI.
You mentioned it even matched VT22B.
On AD20K segmentation, yes. Which is remarkable considering VT22B is massive and SAIL was trained on much less vision-specific data.
That's kind of mind-blowing, learning such strong vision features just from predicting text.
Isn't it? And on ARO, for compositional understanding, it was near perfect, actually surpassing other established vision backbones.
So how do they explain why it learns vision so well?
They suggest it's that intense cross-modal alignment pressure during pre-training. To predict the text accurately, it has to learn semantically rich visual features.
Okay, so it's not just a decent MLLM, it's a potent vision learner baked in. Now, back to the title, Scalability of Simplicity. Do they actually show sale scales better?
They did. They ran controlled experiments, comparing sale against a modular setup. This modular baseline used a SIGLIP encoder.
Which itself was trained on, what, 40 billion samples?
Yeah.
Huge pre-training.
Exactly. And they used the same base LLM architecture as SAIL for a fair comparison.
Okay, so what happened when they varied the amount of MLLM pre-training data?
At low data scales, like 32 million pairs, the modular model did better, probably thanks to SIGLIP's massive pre-training.
Makes sense. That head start matters.
But as they scaled up the data for both to 128 million, then 512 million pairs, SAIL showed a much steeper improvement curve.
Ah, so it learned more effectively from the additional data.
Yes. By the 512 million mark, SAIL's performance caught up and became comparable to the modular one.
So the rate of improvement with data was higher for SAIL.
Exactly. That's the evidence for superior data scalability. It suggests that with enough data, the simpler unified architecture might actually be more efficient.
That's a really important finding. Data might eventually trump architectural complexity here.
It certainly hints that way. A very promising direction for scaling future models.
The paper also mentioned a vision-centric information flow. What does that mean?
They analyzed where the model puts its attention when predicting the next token. They compared SAIL to modular models like Quint2VL and LLaVA.
How did they measure that?
Using a method called FastV, they look at the proportion of attention scores going to image tokens versus text tokens, layer by layer.
And what was the pattern for SAIL?
Single transformer models like SAIL consistently allocated way more attention to the image tokens, like 60 to 80% across the layers.
Wow, that much, compared to modular models.
Modular models were much lower, around 10 to 30% attention on image tokens. Even in controlled experiments, SAIL showed significantly higher attention to vision.
So the conclusion is?
Single transformers like SAIL seem to rely more directly, more heavily on the visual information when making predictions. Vision plays a more dominant role.
A more vision-centric processing pathway. Does that translate to specific task strength?
It seems to. The analysis showed SAIL excelled particularly at tasks needing spatial reasoning.
Like object positions or physical relationships.
Exactly. It outperformed the modular baseline significantly on the MME position split and MM-bench physical relation. Suggests a tighter coupling of visual geometry and language.
Okay, so strengths in spatial understanding. Where did it lag?
It showed weaker performance on tasks demanding a lot of world knowledge. Things like identifying celebrities or specific artworks in the MME benchmark.
Why would that be?
The likely reason is the pre-training data. Modular models benefit from the huge knowledge baked into their pre-trained encoders like CLIP or SIGLIP, which have seen incredibly diverse data. SAIL's pre-training, while large, might be less diverse in those specific knowledge domains.
So potentially solvable by scaling SAIL's pre-training data diversity further.
That's the hypothesis. It's a trade-off, perhaps. Stronger grounding in the immediate visual input, but maybe less access to vast, abstract world knowledge compared to models leveraging giant pre-trained vision components.
Interesting trade-off. What about the Ablation Studies? Did they confirm the importance of those design choices like mixed attention?
They did. They ran tests on a smaller SAIL model, SAIL Byte 0.5b. First, they compared bidirectional attention plus MROPE for images versus just causal attention plus 1D positioning.
And the result?
The bidirectional attention with MROPE gave significant boosts, especially on tasks like text-free QA. It really confirmed the need for rich cross-patch interaction for good visual grounding.
Makes sense. What else did they ablate?
The interleaving of pure text data during pre-training. They tried removing it.
And performance dropped.
Consistently across benchmarks. It really underscored how important it is to keep refreshing the language capabilities in these unified models. You can't just focus on the vision.
So those core design choices seem well justified by the ablations. Did they show off some examples of what SAIL can do?
Oh yeah, the appendix has some great qualitative examples.
Like what?
Really impressive stuff, like extracting complex information from OCR-rich web pages, generating detailed descriptions of busy real-world scenes.
Does it handle charts and things like that?
Yes. understanding scientific charts and graphs, even comprehending posters with mixed text and images.
And did they visualize the attention, show where it's looking?
They did. Figure 7 shows attention maps, illustrating how the model focuses on relevant image regions when generating text, confirming its grounding ability visually.
Sounds very capable indeed. Okay, let's wrap this up. What are the main takeaways for our audience from this SAIL paper?
I think the core message is that this simple, unified, single transformer approach is a genuinely viable and powerful alternative to modular MLLMs.
Simplicity isn't sacrificing capability here.
Right. It shows superior data scalability, which is critical for future progress. It has this distinct vision-centric processing flow, and it learns surprisingly strong visual features directly from the multimodal pre-training.
So it's not just about performance, but also about efficiency and offering new insights.
Exactly. It's a more minimalist design, potentially more scalable, and it teaches us new things about how vision and language can interact within one network.
It definitely feels like a significant step. So here's a final thought to leave you with. Given SAIL's promising scalability and this unique vision-centric flow, what's next?
Right. What architectural tweaks or maybe training strategies could unlock even more potential?
Could these unified models eventually just outperform modular ones across the board? It's a really exciting question for anyone working in this space.
Definitely something to think about. And if you want to dig into the details yourself, the code and models for SAIL are available on GitHub.
Excellent. Well, thanks for tuning us on this deep dive into SAIL.